the record button. Okay. Okay, let's start today's seminar. Today's speaker is Professor Junwu Huang from Perimeter Institute. He'll talk about vortices in muon dark photon. Please start when you're ready.
All right, yeah. So thank you for the invitation and great to be here. And thank you for waking up so early. Yeah, in Korea. So today I'll be telling you about some work I actually did with Will East, who is also faculty here at the Perimeter last year, where we try to understand basically whether we can actually have dark photon dark matter or not. So the talk will mainly about that paper as requested by Theor, and maybe towards the very end, I will also share with you some of our recent progress. It'll be great if you can ask questions, chat, whatever you want, during the talk. Otherwise, so that I don't feel like I'm talking to the void all the time. All right. So the topic today will be about dark photon, and this is a particle that people suggest it will exist dating back to around 40 years ago. And the dark photon is described by this action here, which contains the kinetic term, just like a photon. But unlike a photon, it now has a mass, and as a result, we are thinking about this particle as a dark matter. Its coupling to the standard model is very simple, described by this kinetic mixing parameter epsilon, which mixes the standard model photon and the dark photon in this way. Okay, so it is one of the only dimension 4 operators you can introduce, which couples some particle that can be dark matter with the standard model. So in that sense, it's very interesting thing to look at. So around 10 years ago, the late great Nelson was one of the first people to suggest that if we have a dark photon in the Stuckelberg limit, which I will explain in more detail, can be non-thermal dark matter. And since their suggestion, there has been a lot of work done to figure out all kinds of ways we can produce dark photon in the early universe, either during inflation, through inflation in perturbations. We can produce them through axion dark photon conversion, which is the mechanism that we'll discuss in more detail also today. They can be produced purely gravitationally in the process called black hole superradiance. And it can also occur in some other instabilities, for example, in two-stream instability, which is discussed in both in Jeremy and Martin's talk, and back in 2017, I think, and also in Lazenby's paper, in 2020. So all of these production mechanisms allows us to produce dark photon through some initial instability and populate a large number of dark photon that can be have an energy density that is large enough to be dark matter. So as a function of mass, these mechanisms work in a wide range of mass regions. So the superradiance works at low masses where there are black holes, which has sizes that are comparable to the particle wavelengths, Compton wavelengths. While at higher mass end, we can have inflation in production. So the axion dark photon conversion and the two-stream instability in principle works for almost all the masses of the dark photon, but they require these dark photon particles to be coupled to something else apart from gravity, while these two mechanisms works just with gravitational interactions alone. So both for the reason of production and also we want to actually look for these particles. These particle has better interact with something. And the interaction, for example, this kinetic mixing parameter can be generated through a one loop diagram, first pointed out by Bob Holden in 1985, where basically if you have a charged particle that is charged under both the standard model U1, the hypercharge, or just the electromagnetism at low energies, and also charge under this dark U1. Then through this one loop diagram, you generate the kinetic mixing between these two U1s, which mixes the photon and the dark photon together. Okay, so with this type of scenario, you generally expect that the kinetic mixing parameter is equal to the standard model gauge coupling times the dark gauge coupling over 16 pi squared. So, so that's basically the parameter space that we are looking for this particle. So to say a little bit more, the masses of these dark photons, for example, can be generated from a Higgs mechanism, just like the W and Z. And the UV completion to the point where we are generating the mass for this particle basically leads us to something like a Billion Higgs model, where now we introduce this charged particle phi, which is coupled to this dark photon with a charge under this dark U1. And when this field phi gets a VEV, the dark photon gets a mass, which is ordered G dark times V. So the well-known Stuckelberg limit is the limit where I'm taking the Higgs field to be much, much heavier than the mass of the dark photon. So in particular, like we are taking the m phi squared over ma prime squared, which is basically the quartic coupling over the dark gauge coupling squared to infinity. Okay, so in this limit of large quartic and the small gauge coupling, you can generate very heavy Higgs while at the same time have light dark photon. Okay, and this picture is generally believed to survive as long as you do not go to incredibly high like gauge field strengths, where Schwinger-ish type of production mechanism start to produce like this single particle phi. So, and this critical field where such a particle production can happen is basically the mass of the heavy field squared over the gauge coupling. So like you can think of it as the Schwinger power production, which basically like have a exponential suppression of m squared over E times the field strength. So if we plug in these quantities, what we are getting is lambda to the 1/2 power times v squared. So this is the basically the some sense of like the height of the Higgs potential multiplied by this ratio of lambda over g squared to the 1/2 power. And this is how you see and how people generally believe that when you take the Stuckelberg limit, you decouple the Higgs, and the protag action that I wrote down in the very beginning is a good description of the system all the way to this very high field stresses that can be decoupled. So what I'm going to tell you in this talk is that this picture is not complete. And in particular, I'm going to show you that actually none of the production mechanism of U1 dark photon dark matter is valid. And the problem is that when you break this U1 gauge, well, when you Higgs this U1 gauge symmetry, you not only have single particle states, but you can also have vortex strings. Here we will be talking about gauge strings, but in general, they are described by the number go-to action, plus their interactions with the background field. So what I'm going to show you is that these seemingly long and very heavy defects, topological defects, are actually more likely to be produced in a dark photon, U1 dark photon background, much more than these single particle Higgs states. And this might sound counterintuitive because if you have worked in collider, you understand in a collider, this is super hard to produce things like a monopole. The production cross-section is exponentially suppressed because these monopoles are composite objects. But in our particular example, we'll show you that these heavy defects are actually more likely to be produced compared to single particle states. So in more detail, I'm going to show you that as I raise the energy densities stored in the dark photon field to some critical value, what we are going to see first are these vortex formation dynamics. and how after the vortex formation, they will interact with the background field and it depletes all the dark photon field you try to produce in the first place. Okay. Towards the end, I will be telling you something.
Excuse me,
Yeah.
before you proceed further. So you are now considering only a dark sector without any kinetic mixing or Higgs boson interaction.
Any kinetic mixing. So the model that we'll be considering is just the abelian Higgs model.
Abelian Higgs model in the dark
The
sector.
Stuckelberg. Huh?
Abelian Higgs model in the dark sector and the Stuckelberg limit.
Yes, and we are not coupling this U1 to any charged particles apart from the Higgs, or like none of these dynamics depends on like whether they couple to the center model.
My question is whether you include any interaction with the standard model particles or not through the kinetic mixing or Higgs boson interaction.
It doesn't matter.
Okay, it doesn't matter. Okay.
Yeah. So these dynamics has nothing to do with the center model.
Sure.
They are purely like the dark sector dynamics, and introducing or not interacting with us doesn't really change the picture at all. Thanks for the question.
Thank you.
Yeah.
Thank you.
So we'll show you like some interesting phenomenological consequences of these instabilities in both the case of dark photon dark matter when we are trying to produce some background field like in the early universe, or like we are trying to produce dark photons through the superradiance instability. So that's basically the plan of the talk. Any questions for now, before I move on to the details? Okay. All right. So the first part, I will be showing you how vortex form during dark photon production, or like how vortex form in general. So in the case of where we are trying to produce these dark photons through inflation, all you need to produce the dark photon is gravitational interaction, and all you need to produce these strings are actually also gravitational interaction. So the production of these strings are described by basically, you basically use the number go to action, and the string production rate is basically exponentially suppressed by the string tension over the inflationary Hubble scale square. And these results are dates back to also 30 years ago. So here, what you are seeing in this equation is that if I have string tension that is much smaller than the inflationary Hubble scale, then strings will be produced in the early universe with during inflation with a large abundance. And if I write this condition in terms of these coupling constants, what it tells us is that as long as this dark gauge coupling, which also changes the, which it determines how much like this U1 interacts with anything else, is larger than 10 to the minus 22 EV, 10 to the minus 22 for like a dark photon of order EV masses. These strings will be produced in the early universe if we want to produce these dark photon as dark matter. Okay, so this is a very tiny gauge coupling, and generally, like you will think like you are going to produce these strings during inflation. Of course, producing these strings is not a problem. Well, we know we can search for cosmic strings, and we haven't seen any. Like that's not a problem. The problem, as we'll show you later, is how these strings interact with the background gauge field. But for now, what you need to take away from this slide is just it is very easy to produce these strings if you want to produce a dark photon during inflation for gauge couplings that are extremely tiny even. So the case of the transverse mode is much more complicated. And there are two mechanisms where we can produce these transverse mode dark photon. And transverse mode dark photon are basically like photons. So they store their energies either in their magnetic field or electric field. So there are two mechanisms that produce this transverse mode. The first one is axion dark photon conversion, and the idea here is you wait for some time until at some point the axions start oscillating, and if it is coupled to the dark photons through AFF tilde, both with a primed interaction, then this oscillation of the axion is going to produce through a tachyonic instability dark photon as it is oscillating. And in, for example, this paper by Pratik, they showed how this tachyonic instability will be able to transfer order one or like most of its energy density from the axion to the dark photon. In this production mechanism, initially at least, most of the energy that you produce goes into magnetic field of the dark photon. So the second way that we can produce dark photon is through what is known as the superradiance instability. And this is the instability around a spinning black hole. And if I have a particle whose Compton wavelength is a little bit larger than the black hole horizon, then there is a classical instability which basically transfer the black hole's spin and also as a result its mass into the cloud of particles around it. And this is exponentially growing process which can populate the black hole surrounding with a huge amount of dark photon within a very short amount of time. So here is a video which shows how this cloud is growing as the black hole is rotating around. Okay. So in such a process, what you are producing is a particular trapped particle mode around the black hole, just like hydrogen levels around an atom. And this mode features electric field more than the magnetic field through this superradiance production. Okay, so both of these production mechanisms produce dark photon, either with more electric field or magnetic field. The details of these production mechanisms doesn't matter very much as long as they produce a large amplitude of transverse modes. I will show how these production eventually leads to the formation of vortices in both systems. Okay, so these are the two systems that we are interested in. Where we are trying to where we are producing transverse modes of dark photon. So now the question that I want to understand is that in these systems, how does vortices actually form? So to explain this in more detail, I'm going to take you onto a detour into condensed matter literature. We'll be looking at a bunch of superconductor literatures. And given what has happened in the last 2 weeks, I'm sure like you guys are all very, very familiar with all the superconductor literatures. And given the whole excitement about what might be going to happen, like with the room temperature superconductivity. But I'm still going to assume that you know nothing. So let's start from the very basics, the Landau-Ginzburg model. So the Landau-Ginzburg model is actually the most effective theory or phenomenological model which describes the behaviors of the superconductor. And that is described by the free action, free energy, which has an action, which is basically similar to the action of the Abinich-Higgs model. So the only difference is that it is a free energy, so there is no time dependence. So the free energy describes scalar charge under U1, and the scalar, as you know, is basically the famous BCS Cooper pair. So I have taken the the Fermi velocity to equal to 1, just like we always take a C equal to 1 in particle physics when we are describing the dynamics of the system. Okay. So with this free energy, there are two types of superconductor that can exist. So there's a type 1 superconductor, which is basically when the quartic coupling is smaller than the electric charge square. So in this case, what you have is two phases depending on the strength of the B field. If the magnetic field is very, very small, then what you have is the Meissner effect. The superconductor will repel all the magnetic field from its inside. Well, if the magnetic field strength is much, much bigger, bigger than this critical B field BC, then what happens is that the B field basically goes through the superconductor everywhere, and the superconductivity is lost everywhere. Okay, so that's the critical magnetic field strength, which is equal to lambda V squared over E. Okay, so in the other regime, if the quartic coupling is bigger than E squared, or in their language is the case where the magnetic penetration depth is larger than the coherence length, then what you have is something that is more interesting. So like when we have like a really, really tiny magnetic field, again, we have the Meissner phase, and when we have a really, really large B field, we always have the phase where like the superconductivity is totally lost. But what happens but now in this regime where lambda is bigger than E squared, these two critical fields are not the same. And you can see that BC2 is always bigger than BC1 in the case of type 2. So there is something more interesting that is happening in between, and what is happening is the famous Abrikosov vortex or Abrikosov lattice states, which was first discovered in 1957, where he showed that basically the ground state for magnetic field strengths in between these two critical B fields are these states which contains these vortex solutions. So let me describe to you first like a single vortex. A single vortex has basically the field structure like this. Okay, so the blue is the field profile of the Higgs field, phi of r, while the red is the profile of a magnetic field, the B as a function of r. So the vortex, in the vortex center, the Higgs field has a field strength, field value which goes to 0 at r equal to 0, and it goes back to phi equal to V over a distance of order the mass of 1 over the mass of the Higgs field, 1 over m phi. Well, on the other hand, the magnetic field has a profile which peaks at the location of the vortex, and the magnetic field is changing on a length scale which is set by the mass of the photon in the phi equal to V vacua, and that is basically the magnetic field penetration depth 1 over ma. Okay, so in a type 2 superconductor, the 1 over ma is bigger than 1 over phi as a result of lambda bigger than E squared. So this field profile contains magnetic field, which when you sum over all the magnetic field going through this vortex line, you get a quantized value, and that quantization is can be expressed as basically the quantization of the A mu around the vortex integrated over a circle is equal to phi 0, the unit magnetic flux, which is 2 pi over here 2e, and the reason for 2e is because the Cooper pair has charge 2, made of 2 electrons. So so that's basically a single Abrikosov vortex, and the ground state at intermediate magnetic field strengths are these vortex lattice states, which are basically these single vortices separated with a fixed distance from each other. And the red, again, is the magnetic field profile, while the blue is the profile of the Higgs field. So first, now let's see like some limits. So first, let's take the limit where I'm taking B all the way to BC2, which, as you remember, is lambda V squared over E. So when we plug in here, this quantity basically becomes 1 over m phi. So what it means is that at this second critical field, these vortices are getting closer and closer to each other, and finally they overlap with each other. And basically, like the vortex is everywhere, and phi equal to 0 everywhere, and the superconductivity is totally lost. So this transition above BC2 is a continuous transition. Well, on the other hand, if we take like this B all the way to BC1 or even smaller, clearly like the state with multiple vortices is quite different from the state where I have a uniform superconducting state. So you would imagine that the phase transition around the point BC1 would be a first order phase transition, or like you need to pay an action to tunnel from one vacuum to this ground state, like from the Meissner phase to the ground state. However, though like the phase transition is a first order phase transition at BC1, the phase transition becomes more and more becomes a classical phase instability or second order phase transition once you hit some intermediate magnetic field strengths, the superheating field strengths BSH. Okay, and at this point, there is a new classical instability which develops, which was first pointed out by Galacco in 1966. So here, let me show you what is going on. So let's imagine that I start with a uniform or uniform magnetic field strength and uniform phi field value which satisfy this equation. Now let's say like I have a small perturbation at a point here which makes this B field a little bit bigger. What happens if you look at this equation is that at this point, the B field is a little bit bigger, so the phi value is going to be a little bit smaller, so the blue will have a dent like this. So the phi value controls the mass of the photon in this region. So MA, which is equal to G times phi, is going to be a little bit smaller in this region. And through the Meissner effect, you know that the magnetic flux wants to cluster in this region where the mass of the photon is the smallest. So the B field continue to grow in this region, and the phi continues to drop. And this classical instability or this tachyonic direction will develops until at some point phi has nowhere to decrease when it hits zero. And in this process, what you have essentially formed is a vortex at the location here. So what Galacco showed, and what I'm going to show you in more detail with simulations, is that above the superheating field strength, vortex would form classically. Okay, so that's all I want to say about superconductor. And here's the summary. So what we have explained to you here is there are multiple critical fields which governs the dynamics of these vortices lines. So the most important one, as we were seeing earlier, is the superheating field strength, which controls the point where the vortex forms. Okay, as we'll show you later, the first like a BC1, the first critical field governs the evolution of the vortex after they form. While the second BC critical field strength, BC2, is something that you are more familiar with. This is more like just like the Schwinger field strength about which you can produce single particle state. Okay, and it corresponds to the point where like superconductivity is totally lost. So actually, like in most of the discussion later, we are not going to say anything about BC2 because and now the system we can simulate can actually hit that field strength because they all crash when once we hit the superheating field strength. Okay, so you might ask, like, why don't we just stop here? Like, you told me, like, what type of field strengths I will start having vortex formation, and what field strengths controls their evolution. So now I can just use this to do the analysis analytically, in the case of the dark photon. Well, there are a few critical differences, the biggest difference between like these two systems is actually the fact that superconductors, they are a piece of material, they have an edge. So outside the superconducting material, it's vacuum, and there's just like no superconductivity. Well, our universe, which contain, for example, the dark photon, dark matter, has no edge, right? So there's you cannot just push this vortex line or its energy density outside the universe. That thing cannot exist. So this is the first critical difference, and it leads to two small differences. The first one is the initial state for this phase transition, or this instability, is in the case of dark photon like a coherent background, while in the case of the superconductor, some Meissner phase where all the magnetic field lines are expelled.
So question. Yes.
Yes.
So in this schematic diagram, when you take a Stuckelberg limit,
Yes.
this the gap between BC1, BS super heating, and then BC2, the gaps between these three scales are very large, right?
Yes.
And are you staying, so in the Stuckelberg limit, you are staying below BC2, or you still go up to BC2?
So like, yes, so like let me give you a quick like answer. So basically, like, if you want to have like if you want to produce dark photon, dark matter in the early universe with a appreciable amount, you ought to, like, always be above B at superheat.
Yeah.
There are many models which allow you to be below BC2, but what we are going to show you is like BSH superheating is actually like the limit where you can put the field strength into the system. And if you do a cosmic evolution afterwards, you will realize that that amount of dark photon is too little to do anything. It cannot be dark matter, basically, for any parameter we can choose.
Okay.
Yeah. So that's basically the yeah. So, and it is because like when you take the Stuckelberg limit, like this is so much bigger than that, right? The BC2 is so much bigger than that. So originally you think like there's no problem if I can produce field all the way to this field strength, and after some like a long time of redshifting, I still can have dark photon, dark matter. Well, if this is the limit at any time in the evolution of the universe, then you don't produce enough. Okay, so yeah, so back to this differences in the two cases. So the second difference is that the strings in the case of the superconductor can end on the superconductor edge, right? And the magnetic field just get released into vacuum outside, or into the atmosphere outside. Well, in the case of the universe, the edge also doesn't exist. So the strings will have to be produced with loops. So there are other things, and the more important one is the fact that in a lot of systems, there are a significant amount of electric field existing as the initial condition in the case of dark photon, dark matter. While for superconductors, certainly we are not sustaining a constant electric field all the time. So for all these differences, we try to understand if the same behavior still happen if we set up an initial condition which is more like dark photon, dark matter. So that's the end of the detour. I'm going to show you some simulation result of the vortex formation. If there are questions now. Okay. All right, so let's go on. So now let's show you some results of this vortex formation. So the first simulation I'm showing you is a simulation actually of a superradiance cloud. where this color hue is basically a superradiant cloud, which is rotating around a spinning black hole and growing strength. And what you are seeing here is a green string which showed up all of a sudden as a loop, and this loop continues to rotate around the black hole. Does something eventually, until it eventually, because of the gravitational attraction of the black hole, gets reabsorbed by the black hole. So this video, if we just look at the very beginning, is showing something basically in this plot. As I'm increasing the background field strength, most either the electric field or the magnetic field, depending on the location, once they hit some critical value, there's a jump of this phi field to phi equal to 0, where like a vortex has formed. Okay, so at this point, t equal to 0, we can take a snapshot of the video and show you both this equator picture and also a slice along the longitude. So here, what you are seeing is a vortex string which has formed as a longitude, and it intersects with the equator on 2 points. So this point, as you can see, the phase of the scalar field goes from 0 or minus pi to pi. So like white, blue, black, and red. So it goes a full circle, and this is a location of a topological defect which has formed, and same thing you can see here. Okay, so in the plot on the bottom, what I'm showing you is the value of the phi field as a function of location along a string. So here, what you're seeing, the circle is basically a string where phi is equal to 0. Okay. So here, as I promised you, like what you are seeing is a vortex string has formed at this location t equal to 0. Okay, so that's the case of the superradiance. It does happen at the field strength that we predicted to happen. And the same thing happens if we set up a system where the magnetic field is a little bit bigger than the E field with this axion dark photon conversion. So in this case, again, like you see the field strength is growing, and at this t equal to 0, we can take a snapshot, and what you are seeing in this 2D simulation is a bunch of locations where the field goes from 0 to pi, and here there's a vortex line. There are many vortexes everywhere, like in this plot, and they all form all at the same time. So that's also a simulation which shows you that vortices has formed. Okay, so the take-home message of all of these discussions, including this detour, is that either during the inflationary dark photon production, maybe you already forgot about that, like the longitudinal mode that I explained in the very beginning, or like during the production of transverse dark photon field, either through the superradiance instability or through this the axion dark photon conversion, you are going to produce, in these processes, you are going to inevitably produce some vortex lines.
So when you one question.
Yeah.
So when you say in the previous slide, when you say this inflationary dark photon production, etc., this is for example the production through the mechanism studied by, for example, Rajendra and al.
Yes.
Kaplan, yeah. Or,
yes.
I mean, so from the time-dependent metric.
Yes.
Okay.
Yeah. Exactly. Okay. So so again, as I said earlier, producing a string is not a problem as long as it doesn't interact with dark photon. Unfortunately, it's not the case. And to show you how they interact, let me just walk you through this plot. So what you're seeing here is a vortex string, which is pointing into the or out of the board. That is not important. And the red circle is basically the the circle which encloses the unit magnetic flux. Okay, so this vortex string around it, you can write its A field, which basically equal to theta hat over the gauge coupling times R. So from if the string is moving, you can compute the electric field as basically dA dt, and it is equal to the velocity times the nabla of A vector. And you can take this equation and you can plot it, and that is the orange lines. And if you stare at it, you will realize that this field is basically the electric field of a dipole in 2 dimensions. So, and with a dipole moment that is pointing in the y direction, if the string is moving in the x direction. Okay, so that's basically the electric field of a moving string. So, and it basically behaves like a dipole. So now let's put this string or vortex inside.
Sorry, can I ask a quick question?
Yeah.
What is L here? So in the last equation, you were writing dd dl.
L. Oh, that's like the length, like of the string.
Oh, okay. So
Like
it's
electric dipole
okay,
moment per unit length.
Okay, so it's a perpendicular length of the screen. Okay.
Right. So like that's why I say like it's a 2-dimensional dipole. Because
okay.
like yeah, it's perpendicular to the
That's
string direction. Yeah. Thank you for the question. Yeah. So you get like a electric dipole which points in this direction, and if you now put in a background electric field, now like there is a dipole interaction d dot E. So what this tells you is that if my background electric field is very strong, then the string wants to be accelerated in the x direction such that it makes D bigger and bigger, such that the dipole interaction energy becomes smaller and smaller, right? So this is just like in the case of the Hall effect, when I apply like electric field in the y direction, the object gets the charged particles gets accelerated in the x direction. So, and the physics is actually exactly the same. And so now we have seen this effect. What does it really mean in terms of with the string background field interaction? So here, like what I'm doing is I'm computing the field strength of electric field above which that this interaction is totally controlling the dynamics of the string vortex. Below this critical electric field, or like when the left-hand side of this equation is smaller than the right-hand side, then the right-hand side, which is basically the tension of the string, is determining the evolution of the string. So if the right-hand side is bigger, like then the string is basically oscillating because it has a string tension. While if the left-hand side is bigger, then like this electric background electric field is just pushing the strings around as if like the string has no tension at all. And if you just take this equation and equate, what you're going to find is that the transition between these two behaviors happens at electric field, which is basically this dark gauge coupling times V squared times the log. Okay, so this is basically the first critical field that I was showing you earlier. So why is that, right? So why does the string do something despite like I'm taking like this coupling to 0? Well, the reason is that this vortex line is actually a magnetic object. So the coupling of this magnetic object is more like a monopole than like an electric electric charge particle or a single particle Higgs mode or anything like that. So for a monopole, if I'm taking the electric charge to 0, electric gauge coupling to 0, the magnetic coupling becomes actually infinitely large. So in this process of taking the dark gauge coupling to be smaller and smaller, the strings, they don't decouple. They actually couple more and more, and that's the reason why this critical field becomes smaller and smaller. Okay, and this critical field, of course, is extremely tiny in any time of the universe. Okay, so let's show you a simulation which shows a little bit better like how this electric field is at work. So here what you're seeing is the strings form, and after it formed, there is still a lot of energy stored in the background field of the superradiance cloud that the field just pushed the strings out to be a much larger loop. Despite that the black hole is trying to attract it and to collapse it onto the black hole through gravitational interaction. So, and this is, you can see in more detail in this figure on the right, where you see after the string production, the vortex line takes away almost all the total energy from the system, while the gauge field will decay away very quickly. Okay. So the same similar behavior also happens when we do this cosmological simulation of axion dark photon conversion. So this is what happens in the very beginning when we produce a bunch of vortex lines at some t equal to 0 after the vortex formation. In this 3D simulation, what we are seeing is that the energy that is stored in these vortex lines continue to grow as it absorbs the energy density inside the background field, while the energy stored in the background field will decrease until like it hits BC1. Okay, so that's basically the dynamics of the system, and the take-home message is that the dark photon electric field will make the strings faster. The magnetic field will make the strings longer. This I didn't explain in detail, but like it's very easy to see. And after some time, like all of these background fields are gone, and all of the energies gets absorbed by the string network. Okay, so this basically completes the first important message from this talk, which is that the dark photon dark matter is gone.
Before you proceed, one question. So, are there any difference between the transverse dark photon and the longitudinal dark photon modes?
So yes, like there are. So actually, like if you think about the longitudinal mode, right? Like it is basically derivative of this theta, which is this U1 direction,
Yes.
which form the string. So when you are saying you are producing a lot of dark photon longitudinal mode, what you are trying to basically saying is you are trying to like go through the circle anyway.
Mm.
And it's very easy to see like when you are trying to produce the longitudinal mode, like once you produce a large enough amplitude, you basically complete the circle and the vortex will form. So in the case of the like a transverse case, like it's much harder to see that these vortex form. They need to go through this instability that I was explaining to you earlier to form. But eventually, like what we are showing you is that it forms as well. Yeah. Does this answer your question?
Okay. Yes.
Okay. All right. So that's well, in principle, I can just stop here because that's the even like the most important message. But then like you can also still ask that like what is happening after this vortex fluid has formed. Okay, so what type of phenomenology does the system actually lead to? And that is going to be the second part of the talk, where I'm going to show you how these vortex strings, after they have formed, evolve afterwards. And the interaction which governs this dynamics is string crossing. And basically, if you have two strings which cross each other, they can exchange their partner and through interaction like this. So what this interaction allows you to get is starting with long strings. If the string is quite wiggly, form a bunch of small loops. Okay? And the melting phase transition is basically the phase transition where people realized after this superheated phase transition, the vortex lines will interact very significantly with each other, forming a lot of small loops. And the small loops are now correlated with each other on large scale, and as a result, you are decreasing the long range order. and hence the name melting. So here is basically what I was just saying, and this is an active area of research. Actually, this is a plot I took from a review article in 2021, where they are trying to characterize the decreasing long range order in actually high TC superconductors. So the same behavior also, of course, happens in both dark photon dark matter and also in the superradiance case. And here, like, I'm going to basically tell you what the consequence. So first, let's see these two plots, which are basically two different time snapshots of the simulation of the string network we run in 3D. So the one on the left is a little bit earlier, while the one on the right is much later. Okay, so what you are seeing is that there are much more small loops that has formed in the system compared to the earlier snapshot. So the average string length decreases, and the energy as a result can be, for example, dissipated into gravitational wave or dark photon radiation as these loops are oscillating. So we think like the dominant energy density, the dominant channel that this energy density will eventually be released in are gravitational wave. And these gravitational wave mainly coming from the oscillations of long strings or a bundle of long strings, and through their coherent oscillation, they emit gravitational wave in the process. So you will say like, okay, this is not what I usually think. Like actually, for any string that is not purely number gauge string, for both axion strings and also for gauge strings, most of the energy actually goes into dark radiation. Because through this emission, like you do not need to pay G Newton as a suppression. So so the reason that and it is true that like the small loops, like when you just leave them on their own, like they are going to mostly give you dark electromagnetic field instead of gravitational radiation. However, when we look at it in more detail, and this is some preliminary result in this collaboration with Anson Hook and his students, is that these emissions of these gauge fields will quickly put the energy density in the background radiation above the first critical field strength, by which time the back reaction of these fields onto the long strings which are still surviving is not negligible. And if we estimate how long does it take for the back reaction to be no longer important, it usually takes a huge amount of time for all of the parameter space that we are interested in. So the picture that we think is actually happening is this triangle, like I'm showing you here. So through the melting phase transition, through the string crossing, what you are getting is from long strings, and you are you are producing a lot of small strings, short strings. And these short strings, they are the dominant emitters. They are going to emit a lot of radiation into dark photon gauge fields, and these gauge fields, once they are emitted, they are going to push on the strings that are still existing and making these strings longer and faster. And this cycle continues, and through for a long time, during which period, like you are constantly producing gravitational wave, which is the only channel you can actually take energy away from the system totally. So so we are trying to understand like these dynamics in more detail, and which will probably hopefully allow us to have a better prediction on the gravitational wave spectrum. We can compare with these sensitivity curves. Yes. Yeah. Any questions? Oh, okay. Sorry. Okay, so so that's the case of early universe. If you are producing a string network, what happens? In the case of the late universe, when we are producing this string network in a superradiance cloud, what happens is that after these strings are intersecting with each other, they not only exchange partner, but they also exchange momentum, right? So whereas a string, which like in the videos I was showing you, has a symmetry around the center of the black hole when they form and throughout their evolution. And like the center of mass momentum is exactly equal to 0 at any time, which is why like they eventually has to collapse onto the black hole. For most of these loops, which has interactions with other strings and exchange their partner with the other strings, then these new form loops would not have 0 center of mass momentum, and as a result can be ejected. So this ejection can lead to a huge amount of strings that are propagating out of the black hole environment, which is the process that we call Bose-Nova or string Bose-Nova. So in such a process, basically what you are ejecting are these string loops. There are certain things which are very well understood, like the average length will be order 1,000 kilometer. The radius of a loop will be order 100 kilometer, which are basically all of order the size of the black hole, solar mass black hole. While the string tension and the number of string can vary by a huge amount depending on the ratio, how much in the Stochastic limit you want to take your system. So in the case where this ratio is small, then you can have in principle like strings, which can have a tension that are large enough to get G mu of order 10⁻⁵. So these are things that would have already been excluded if they are existing in the universe everywhere, right? Because they are producing too much anisotropies in the CMB. Well, because we are producing these things in a localized environment around the black hole, like all of these cosmology constraints that apply, and you can get like a instant burst of the gravitational wave with a humongous strength from the string if they ever get emitted from the black hole. So on the other hand, you can have if you are taking like the limit where lambda over g squared is very, very large, then the string tension is very, very tiny. But in this case, then the number of string which goes as lambda over g squared will becomes very large. And in principle, we can have like order 10 to the 40 string leaving the black hole system all at once. So in the first case, where this ratio is more close to something like 100 to 1,000, then what you can have is the emission of a very high tension string loop. It will oscillate and release a lot of energy into gravitational wave that can be, for example, look for like with the advanced LIGO. This is the string, an estimate of the string, and it is way above. If this is actually what is happening, then it will cause like the detector to do something really violent. The estimate basically shows us that we can see these string Bose-Nova event for black holes anywhere like in our galaxy in the LIGO band. In the other limits, when we have this ratio become very, very large, then the string tension is really tiny, but the amount of strings that you're emitting at the same time is very, very large. And what this leads to is that even after some kiloparsec of length of propagation, they are still overlapping each other, which means they are still in this strongly interacting regime that I was telling you, strong back reaction regime that I was telling you earlier. So in this case, you can have these strings all the way coming to us from somewhere like a 10 kiloparsec away, and you can have a flux on the Earth, which is order 10 to the 10 per year. And these objects will be hitting, for example, also your gravitational detectors or any mechanical resonators and leave an imprint. And that is also something that we have been looking at. And so these are some preliminary plots made by Creighton, and where we show that for many different combination of the parameters, we can have like these topological defects, which flies all the way from the center of the galaxy to us, and leaving some interesting glitch-like signals in gravitational wave detectors that we can model. So these are some ongoing work. Hopefully we'll get this out soon. All right, so that's all I want to say about this vortex system. So there are other things, very interesting things that can happen in a superradiance cloud. And this is a paper that I wrote with colleagues at Perimeter and Marsha, well, actually later, December last year, where we show that if you have a dark photon superradiance cloud and you have a kinetic mixing parameter, then you can also have an object that looks very much like a pulsar but much brighter. So you can do follow-up studies to LIGO black holes. If you're interested, yeah, I'm happy to tell you more, or you can ask Christina to give a talk. So that's all. The conclusion is hopefully I have convinced you that if we want to produce dark photon dark matter, or in the case of dark photon superradiance, as the field strength is growing, you can hit a critical field where vortices form, and after their formation, they interact with the background dark photon dark matter field, gets its energy from the background field, depletes the dark photon dark matter if you want, or like it takes away energy from the superradiance cloud, gives you and this leads to interesting phenomenological consequences, including early universe gravitational wave emission, and also these string Bose-Nova event, which can lead to both gravitational wave signals and also string loops that come all the way to you. And hopefully we can find some of those. That would be very exciting. All right, that's all I want to say. These are some of the one example of interesting collective dynamics that can happen in well, bosonic dark matter systems, or any systems which have a large occupation number, or any dark matter system. And it's kind of interesting that if we think like these classical objects can lead to interesting signatures that that would otherwise be impossible, like if we just think about dark matter as single particle states. And that's all I want to say. Thank you.
Thank you very much for the nice talk. Any question? So actually, I have one very nice. Okay, please.
Yeah, sorry.
Go ahead.
So thanks very much for the nice talk. So you said that this string formation and they eventually kind of converts the dark photon dark matter into basically depletes the dark matter population. And you also said that it generates a lot of gravitational waves and relativistic fluxes of dark photons, right?
Well, right now we think it's mostly gravitational waves with a small amount of dark photon radiation. Yes.
Okay. So is it then okay to say that like an order one fraction of the dark matter is getting converted into radiation, cosmologically speaking?
Well, it's basically saying like so like at some very early time, if you try to produce dark matter, dark photon dark matter, they will not stay as dark photon dark matter. They were going to be converted into some radiation early on. Yes.
I see.
But this time can be like really, really early on. So like back then, like you know, like if we're doing this conversion when the universe temperature is like a GeV or TeV, right? At that point, like the dark matter is a very tiny amount of the total energy density.
Okay, yeah, right. Yeah,
So
that's
if you are worried about unaffected bonds, those things doesn't exist.
okay, yeah. So it's very early on. Mhm.
So in your actual numerical simulation, are you so you are not working in the Stuckelberg limit, or do you work in the Stuckelberg limit?
Of course I
is it
cannot really.
dynamical or not?
So I cannot really simulate lambda over g squared equals 10 to the 30, right? But
Yeah.
because I need to resolve both length scales. But we can simulate like this ratio equals 400, 600, and then we see like the behavior, like the scaling behavior that.
Let me
As
ask
I-
you another way. So in your simulation, the scalar field phi is dynamical, or is
It is dynamical.
It's dynamical.
Yes.
Okay.
Yeah, but it's a very heavy field.
Yeah.
Do you have any?
Yeah.
Please go ahead.
So if you don't make it dynamical, like then you are going to see this instability happening, but like you are going to just see like something is getting absorbed like into the smallest lattice units of the simulation. But like when you resolve like this field, then like you see like actually this field is doing something crazy at this point. Yeah.
Do you have any comment? I mean, if it forms after the form that string vortex, then form the binary. Is it change the result of the gravitational waves from the binaries, or I mean the strings?
The strings, like once they are ejected, they are gone. Like the binary takes a long time to merge, right?
Right.
Yes. So like the superradiance process is making the black hole spin down.
Right.
So in principle, if you can measure like the initial black hole spin, like you can get some information from the binary. You can get some information about superradiance, but the strings won't be there like when the black hole is merging, for example.
Oh, I see.
Yeah. So it's more like if you have so both like this and also the thing that I mentioned here. What you are imagining is like you have a black hole neutron star merger, or you have a supernova which is producing a spinning black hole. After its production, something is happening. Okay. It's always like after the spinning black hole has formed, then there's the superradiance instability. You can have like either of these two dynamics happening after some time, after a black hole is formed. But not like before, like the merger. Yeah, it's always after the merger.
Is there any other question?
Yeah, I have one from this black hole part also. So, have you calculated the expected waveform of these string events in the gravitational wave detectors? Like how will they look like?
So this case, or like which case? Like the gravitation, like this case?
Yeah, this one.
So to do that, like we need more simulations. Basically, we need to know like what's the power spectrum of the modes on the string as as it is radiating. Then like I can get the frequency spectrum, right?
Okay.
But right now we don't. So I can only tell you like what's the roughly like the frequency and how much total power I'm emitting.
Okay, I see. I was just wondering if you can confuse this event with a merger or something like that.
No, like you cannot because yeah, because it's for like when it is emitting gravitational wave, like it's always in this strongly back reacting regime. So computing like the waveform like analytically is pretty much impossible. But in some sense, it doesn't really matter if your string is like 10⁻18, 10⁻19, because no matter what's the waveform, like LIGO is going to pick it up.
I see. Okay.
Yeah.
Thanks.
We just need to make sure that they don't throw it away.
Yeah.
Yeah.
Right.
Any other question? Okay, now let's thank speaker again. Thank you very much.
Thank you very much.
Yeah, thank you.